Good evening, everyone. Welcome to the third live session for the course Advanced Reinforced Concrete Design offered by NPTEL. I am Arshit Agrawal, a PMRF PhD scholar from the Department of Civil Engineering, IIT Bombay, and I will be taking weekly live session for this course for the entire course duration. So, first of all, for those who have joined the session for the first time, what are these sessions all about? So, these are weekly interactive sessions that are held every Tuesday from 6 p.m. to 8 p.m. During the session, we interact by answering the questions that I will ask in the chat box, by posting your queries in the chat box, by raising hand and muting and asking your queries. Apart from the session, you can always use the discussion forum of the course where the questions will be addressed through the discussion forum itself or in the next live session. And attending these sessions regularly will help you to answer the graded assignments easily and will help you to further understand complex topics holistically. Okay, so in today's session, we'll first have a quick recap for week 2 live discussion session that we conducted last week. Then we'll move in. We will have a review of week three learnings. So in the week three recordings that you have listened, it was oriented towards the durability of concrete, where we first had a basic overview of durability, then how concrete quality and aggressiveness of the environment causes durability issues was discussed, along with different ion transport mechanisms, different types of chemical degradation, mechanical degradations, and corrosion of reinforcing steel was discussed. And at the end, how design code incorporates durability consideration while mixture proportioning was presented. So today, along with the quick theory recap of different segments, I will introduce you with several questions to challenge your understanding on these topics. So in total, there will be around 30 questions that we'll discuss today. So that theory part will keep a very quick review so that we can have more time for the questions. And at the end, I will make myself available to solve your queries, any other queries that you have related to the past assignment questions. Whenever anyone has any doubt, you can just type in the chat box, and then in between, when I will stop my presentation, I will have a look. Okay. So last week we discussed about cement, which is a binding material in concrete. We started with lime as a binder. We talked about the history of lime and how it was used in ancient time. We talked about lime cycle, and then we saw how cement came and how it is produced. We saw the oxide composition and chemical composition of ordinary Portland cement, and we saw the hydration reactions of C3S, C2S, and C3A, and how C3A causes flesh setting and why we add gypsum in clinker production or in cement production to prevent the flesh setting. Then we discussed different types of cement in detail. We discussed about different types of ASTM cements and how they differ in chemical composition, in compound composition, and what are their application area based on their composition. We also saw BIS classification of cement apart from this ASTM classification. And then we discussed about compressive strength of concrete, how the stress versus strain profile differ for different grade that we saw. We talked about stress versus strain profile of aggregate cement paste and concrete and how this affects the failure plane. We talked about end plating defect and how it differs between cube and cylinder, and we saw how failure of concrete occurs in compression by seeing the crack propagation, creation of failure plane, and the change in the stress strain profile of the volumetric strain. We discussed multi-axial loading of concrete and how it increases the compressive strength of concrete, mainly due to the confining pressure that is created by the lateral stresses, which nullifies the tensile stresses that are generated when we apply uniaxial compression load. We talked about, apart from this, we talked about MOE of concrete, tensile strength of concrete, and then we talked about long term behavior of concrete in terms of creep and shrinkage. And finally, we discussed about steel reinforcement material, what is the effect of grade on the stress versus strain profile, and how this profile is used in design. We also talked about different types of alloyed and coated reinforcement, mainly in cases where corrosion is a threat. And we talked about FRP bars. Okay, and what is one of the basic problem with those rebars? Okay, so this was what complete story from the last live session. Now, till date, we have talked about individual components of reinforced concrete, the design methods, and the mechanical properties of concrete. Now, the final segment of basic concrete discussion is the durability of concrete. So, when we talk about modern day concrete applications, is having adequate strength enough for concrete design? The answer will be no. Okay, it is a clear no answer. Why? And this is evident from the raising environmental concerns that we see, which leads to premature deterioration of modern structures. Okay, so that's why durability of concrete has become an important factor, as strength of concrete, as important as strength of concrete. Okay, now what is the technical definition of durability? Like, what do you mean by durability? So if we see the definition of durability given by ACI code, so you see they define durability as durability of concrete is defined as its ability to resist weathering action, chemical attack, abrasion, or any other forms of deterioration. So this is what durability as a word mean. Okay, but now when do we say that a concrete is durable? Like, how we define concrete as a durable material? So for that we have a definition that is given by IS code. So what IS code says, a durable concrete is defined as the one that performs satisfactorily under expected exposure condition for a specified service life or lifespan of a structure. Now, if you see here, both these definitions are defining the same thing, but from a different angle. Okay, the first definition that is given by ACI, it talks about what durability mean in terms of resistance to weathering actions. And in the second definition that is given by IS code, it talks about how concrete responds to this weathering action as the definition of durability. Okay, so both are uh, defining the same thing but from a different angle. Okay, now if you see in the second definition, I have highlighted one word here, which is service life. Okay, so it's not like we have prepared a concrete and it will last for lifetime. No, concrete will naturally degrade over time, and that natural degradation is what is considered while designing a concrete in terms of service life. So service life basically defines what will be the time frame till which my concrete will serve its intended purpose. Okay, so the same thing I have written here. Service life of a concrete can be defined as the assumed period for which a structure or a part of its structure to be used for its intended purpose with anticipated maintenance, but without major repair when necessary. So what this definition means, suppose you have designed a building which was supposed to serve as a residential apartment. Now over time, due to degradation of that building, the quality of concrete or the service of the concrete won't be sufficient to fulfill the need of a residential apartment. So suppose that building has now been used for some other functionality. So it we won't say that it is still in its service life. No, service life means that whatever intended purpose which was fixed at the start, it should be able to serve that purpose only. If the concrete is not able to serve that purpose, then the service life has ended. That is a key point in service life definition and in durability definition. So you see here, IS code also mentioned this clearly. Performs satisfactory under an expected exposure condition for a specified service life, for a specified application also. Okay. So if there is degradation apart from the pre-planned degradation, what will happen? The service life of concrete will reduce. Okay. So this figure just simply explains that degradation or deterioration that we are talking about. So if you see the gray dotted line, it shows how the performance of concrete will degrade naturally. So this line is naturally how the concrete degradation is happening. And this point, so we have a critical performance limit that we have defined in a concrete. So when this critical limit is reached, we say that the service life of infrastructure has been reached. Okay. But suppose if there is extra unplanned degradation that is happening, then what will happen? This performance of concrete will degrade at a faster rate compared to natural degradation. And so this critical performance level it will reach sooner than it should have been uh, breached. Okay, so you see this difference in these 2 points. It is the loss in service life of the structure due to deterioration. Okay, so the this is what this is why durability is important, so that we can bridge this gap to a minimal value. Okay, and to counter this degradation, there is repair, retrofitting, and rehabilitation that is done. So if at timely interval I am checking my structures properly and I am implementing measures to improve or restore its performance, then I can again increase the service of my structure to what it was intended at the start. Okay, so this green dotted line, it shows you the service life or the performance of a structure if proper repair and retrofitting applications are implemented from time to time. Okay, so that's why in the definition of service life, it is said that anticipated maintenance is also a part of service life. Now, on this slide, you can see a basic flowchart that describes both definitions that we have talked about. So, durability is a function of both concrete system as well as the aggressiveness of the environment. Okay, and the concrete system is governed by the quality of concrete. Okay, so when we talk about concrete system, the quality of concrete is the thing that is important to us when we talk about durability. Okay, now this concrete system, the quality will depend upon both the material that is used and the process of preparation of concrete. Okay, so the material, by material I mean the binder type, binder content, aggregate, admixture, and mixture design. All will define the quality of concrete. And the process, by process I mean how the mixing is done, how the transportation is done, how the compaction is done, whether it is cured properly or not, whether it is cured in adequate temperature or not, and whether proper workmanship was ensured while concreting. It will also define the quality of the concrete that is produced. And if there is a poor quality concrete, there will be high risk of durability. If there is a good quality concrete, the risk of durability will be reduced. So this is the concrete side of durability. And the aggressiveness of the environment decides the degradation or the deterioration of concrete, even for a bad concrete or for a good concrete, any kind of concrete. So aggressiveness of environment again can be divided into two categories. It can be physical or it can be chemical. So in physical we have abrasion, erosion, cavitation, and freeze thaw that we'll discuss later in this session. And by chemical, we mainly mean to say the ingress of aggressive ions or chemicals which can hamper the quality of concrete. They can cause dissolution in concrete. They can cause leaching in concrete. They can cause diffusion of aggressive ions in concrete. They can cause expansion of some products inside concrete, and these all things can lead to deterioration of concrete. Okay, so this is what an aggressiveness of environment can do to a concrete system and can do to the durability of a concrete. Okay, now in this slide you can see some examples of this first part of the concrete system. Okay, what is the effect of poor concreting on the final structure? So this image one, if you see here, it shows the honeycombing in concrete that can come due to inadequate vibration while pouring of concrete. So you see there are different spots here. So that is due to poor workmanship and poor vibration control while concreted. Now this will give rise to durability issues in concrete. In second image, you can see the exposed reinforcement that is present in a concrete slab, in a concrete wall, which was due to poor cover concrete quality can be one reason, or it can one reason can be very low cover depth was provided, which has failed prematurely before the design. Okay, so this can again lead to durability issues. And in the third image you can see this presence of a cold joint that is there in this wall, which can happen if there is a significant time gap between two pours of a concrete mix. So this can also give rise to durability issues. So these are just some example of this second part of process, how process can cause durability issue. Okay, now, based on this basic understanding of service life and the performance degradation over time, just try to answer these three questions. And in between, if you have any doubts till now, just post it in the chat box. I will freeze my screen to the questions for a couple of minutes so that you can answer. Okay, let's see the answer so that we can move quickly ahead also. So for first question, a residual building designed for 75 years shows rapid degradation signs within 10 years. If the mixed used was of high compressive strength and well compacted, what is the most likely reason for early durability failure? So, yeah, there can be multiple answers to this. Improper calculation of load factor can be one answer, okay, which has led to improper grading of concrete or improper strength consideration, okay. And one more answer can be wrong assumption of environmental exposure. So, what happens even for a good quality concrete? The type of exposure also is also very important. So we define exposure and we classify exposure in different categories: mild, severe, moderate. Suppose you have made a well compacted high strength concrete and you have assumed mild exposure instead of severe, then also your service life won't be what you expected. Okay, so that can also be one reason. Okay, because exposure conditions provide limits on different design parameters. We will see this part later on, how this come into action. Okay, so for now you can just remember this. For second question, which factors has the greatest impact on the long term service life of a reinforced concrete structure? So the correct answer will be B, yes. So for second, it will be exposure condition and permeability, which is the correct answer. So when we talk about durability and service life, they are heavily influenced by how well structure is able to resist the environmental attacks. And this environmental attack is mainly governed by the permeability of concrete, like how much concrete is allowing the aggressive ions to pass through it, and by the surrounding condition where the structure is located. Okay, that has the most impact, most significant impact on the service life. Okay, now question number 3, has anyone answered? Yeah, okay, so let's discuss. In a graph showing performance degradation versus time, so this graph I'm talking about here. Okay, in this graph, what does the slope of the curve during the propagation phase primarily represent? So this is the propagation phase. This entire decrease is the propagation. So the performance is degrading over time. That is what I mean by the propagation phase. So the correct answer for this will be D, the speed of deterioration due to environmental attack. So what is happening? If the slope of this line is more, it means that there is higher rate of degradation that is happening to the performance of concrete. Okay, if the slope is less, that means the performance is able to retain for a longer time. That means that the degradation is performance is lower. Okay. Okay, let's move ahead. So talking about durability of concrete, it can happen in several ways. Okay, there can be several reasons which can cause durability issues in concrete. There is mechanical degradation, which can happen due to abrasion, erosion, impact, and explosion. There is physical degradation, which can happen due to freeze thaw impact, creep and shrinkage we have seen in the last session. Due to fire also degradation can happen. Structural degradation can happen due to overloading, settlement, and fatigue. In overloading, like the option that we mentioned, incorrect consideration of load factor, that can give rise to overloading issues. Fatigue is long term effect that can come from creep and shrinkage, and settlement is due to poor consolidation of soil underneath. Okay, there's chemical degradation which can happen due to different chemical reactions that can occur in concrete. There's biological degradation due to foiling and biogenic attack, and there's corrosion of reinforcement steel. Okay, so for today we'll be discussing mainly about this chemical degradation, mechanical degradation, and corrosion. Okay, now among these, both of these categories, chemical degradation and corrosion, they involves the presence of moisture as a key agent for contributing to the ingress of aggressive ions that is passing through the concrete. So lower is the permeability of my concrete, the better it will be able to resist the aggressive environments. Okay, so that's why transport of ions through concrete is also a major point in durability. Now, here, when we talk about this transport of ions or transport of moisture, they can be affected by several factors, which has been clubbed in three categories. First is the quality of cover. Okay, so both cover thickness and structure of pores inside the concrete will govern the rate of moisture and ion ingress. Okay, so lower is the cover thickness. It means more will be the faster will be the penetration to deeper depths, and more are the pores inside the concrete, easier will be the penetration of ions and moisture inside the concrete. Second category is the environmental conditions that will be defined by the ability of moisture in the atmosphere, the aggressive ions ability in the atmosphere, and the temperature of the atmosphere or the surrounding. Okay, so more is the severity of exposure, higher will be the durability risk. Okay, and more is the availability of moisture, then also there will be higher chances of penetration of ions inside the concrete. So these two are direct reasoning that you can understand. Temperature is also a factor. Why? Because it can lead to moisture evaporation and cracking in the cover. Okay, so that's why it is also included in environmental conditions. In hot and humid weather, you see there are chances of more creep and shrinkage effect that can occur in concrete. So that's why that can also give rise to durability issues in concrete. So if there's cracking inside concrete, the transport of aggressive ions or the moisture will become easy because it will provide a direct path. Okay, so in that way, temperature can contribute in the transport of ions. Okay, and the third is the transportation mechanism. So based on the gradient of concentration, pressure, and what force is driving these aggressive ions, the ingress can be driven by different mechanism. It can be diffusion, it can be capillary absorption, it can be permeation, and it can be migration. So each of these mechanisms has a different way of action. Okay, and that is why transport mechanism is also a factor that can govern the ingress of aggressive ions. So here, if you see all these four transport mechanisms and how what factors are what are the factors that influence them. So when we talk about absorption, it is the capillary action. Okay, that is the movement of moisture from higher concentration to lower concentration, and that is defined by the moisture gradient that is present, the capillary pore size, and the pore connection. Okay, so in concrete, there are different types of pores. There are capillary pores, there are macro pores, and micro pores, mainly if we classify. So this adsorption or absorption, it is governed by the macro pores, in which we have the capillary pores. Okay, so how these pores are distributed, what are the size of this pore, what are the size of these pores, and how they are connected, that will govern the ingress of moisture. Okay, Then there's permeation. So permeation is basically flow under pressure gradient. So from higher pressure to lower pressure, the flow of ions can happen, and that will again depend upon the capillary size and capillary connection and the pressure, the amount of pressure gradient which is present. Third mechanism and very common mechanism of degradation in concrete is diffusion, that is defined as the flow under concentration gradient. So suppose my environment has a higher concentration of aggressive ions, and in my concrete system there is low concentration of ions. So due to this there will be diffusion from higher concentration to lower concentration. Okay, so this is defined by the concentration gradient. What is the difference in these two things will define the rate at which diffusion is occurring. Then capillary connections is one thing that will define how fast they are moving inside concrete. The degree of reactions of ions with hydration product is one more thing. There are certain ions which are present in the environment which can interact with the space system inside the concrete. Okay, so that's why degree of reaction of these ions with the space system can also govern the rate at which they are moving inside, and that can govern the rate of diffusion of ions. And then there is migration. Okay, so migration is the movement of ion under an electric field. So the first three category that we saw, it is naturally occurring thing. Migration is something that is forced. Okay, so we apply electric field, okay, using a direct power, a direct current supply, and we force ions to move inside. So suppose there are negative chlorides ion that are present in the atmosphere, so we'll force them to move inside to opposite electrodes. So from this negative electrode to positive electrodes, so these ions will be attracted towards positive electrodes. So we are migrating these ions forcefully towards the steel reinforcement or towards the other side of concrete. So that is what is known as migration, forceful movement of ions under a applied electric field. And this, the rate of migration will depend upon what is the potential difference we are applying. If we apply higher potential difference, there will be faster movement. And again on the capillary connection, so one thing you can see is common in all the four transport mechanism, that is the capillary connection. Okay, how well the pores are connected inside the concrete. Okay, now try to answer these questions based on this transportation mechanism and pore structure of concrete. Okay, let's see the answers now. For question number 4, which of the following statements best explain how the pore structure influences degradation of concrete? Okay, so the correct answer for this will be D. Okay. Okay, so if there are more disconnected pores inside the system, the connectivity of pores will be lower. So that will minimize the transport of aggressive agents or ions through concrete. Okay, someone answered B also. Well connected pore system enhances the water retention. See here, water retention means what amount of water is there inside the concrete. We don't want more moisture inside the concrete. Okay, so this is a negative statement basically, not a positive explanation of how pore structure is influencing the degradation. So here the influence we mean in terms of movement of transport ions. Question number 5, has anyone answered? A bridge pier in a cold region has recently experienced visible surface scaling followed by cracking and rust stains. Investigations reveal poor quality concrete cover. Which of the following is most likely chain of deterioration? Okay, so here the keywords are cold region, surface scaling, cracking and rust stains. Okay, and poor quality cover. Okay, so from this, can anyone predict what can be the reason? What is the main degradation mechanism in cold regions? It is the freeze and thaw effect. Okay, so what would have happened due to freeze and thaw effect? They would have been cracking inside concrete, which has increased the uh, which increases the pressure inside concrete. Okay, which has a this how it is increasing the pressure, we'll talk later. Okay, so cracking might have due to this freeze and thaw, cracking would have occurred in concrete, and which could have led to easy ingress of ions through concrete, and this resulted in corrosion of reinforcement. So that's why we have cracking and then rust stains also. So this can be a likely a chain of degradation mechanism. Okay, so cracking led to easier ingress of ions, which led to corrosion of reinforcement. Now for question number 6, which of the following correctly distinguishes diffusion from capillary adsorption in transport of aggressive agents? So what is the difference between diffusion and capillary absorption? Can anyone answer? Okay, so diffusion is basically it is a concentration driven for phenomena. From higher concentration to lower concentration, it is the movement of ion. However, capillary absorption is a moisture sucking in of moisture inside a concrete system. So it is a moisture driven phenomena. From higher moisture state to lower moisture state when the water movement is happening. Okay, so that is a very small difference. Both is due to concentration only, but these diffusion is more for ions, and capillary absorption is more for moisture driving, moisture transport. Okay, try to answer these two more questions related to the pore contribution of pore structure or pore connectivity of concrete. I'm having headache. Too much screen time in one day. 40 slides left. Okay, let's see the answer. For question number 7, a marine structure shows significant reinforcement corrosion 7 years after construction. The concrete cover is thinner than specified and has a porous microstructure. What combination of factors likely accelerated corrosion? Okay, so it will be option number B. Okay, so since there is a porous microstructure, there will be capillary absorption of chloride ions, of moisture and chloride ions. Okay, which has accelerated the diffusion process, which has reduced the diffusion resistance and accelerated the diffusion process. And since the diffusion of ions was accelerated, that's why corrosion was visible well before what was the plan. Okay, and since the cover is also thinner, then again the ions will reach deeper depths before it should have reached. Okay, so that's why B option will be correct. Question number 8, Capillary absorption increases with which combination of pore properties? Okay, so the correct answer for this will be connected pores and small diameter pores. So generally what happens, this capillary action that we talk, it is stronger in small diameter pores because they provide a higher suction pressure for moisture movement. Okay, and connected pores, they allow continuous transport of moisture and dissolved ions to a deeper depth. Okay, disconnected pores over a large or a large area pores, they reduces this capillary pressure. Okay, so that's a smaller diameter and connected pores will be the correct option. Smaller diameter is generating more capillary pressure for ion ingress, and connected pores is ensuring that those ions and moisture is moving to a larger depth. Okay, in larger diameter pores, that capillary effect is not that strong as compared to smaller diameter pores. Okay, B won't be correct. Why? Because there are disconnected pores. If you want to increase the capillary absorption, we need connected pores, not disconnected pores. Any doubts in these questions? Okay, let's move to the next part. Now, so we saw that transport of ion, that we saw that in transport of ions, it's the poor quality of concrete cover which is a major issue. Okay, so to improve the durability of this cover concrete, it is important to use a good quality concrete. Okay, for the cover. Okay, so in poor quality cover concrete, what will happen? This ions, deleterious ions or deteriorating ions, they will reach the reinforcement fast. Okay, or they will reach penetrate to a deeper depth fast. However, if you will use a good quality cover concrete, this rate of movement of ions will be smaller, will be lower, so we will have a good quality concrete for a longer life. Okay, now how to improve the durability of concrete, how to improve the quality of concrete? This can be done by improving the pore structure of concrete. Okay, and this can be done in either of the three ways: by using a lower W by C ratio, water to cement ratio, by improving the packing density of concrete, or by using mineral admixtures as additives. Okay, so in the first image here, it illustrates how lowering the water to cement ratio improves the quality of cover concrete. So if you can see, when we use a high W by C ratio, there is excess of water that is present inside my system, which creates porous and weak microstructure after hydration. So you can see here there are more gaps that are present, more pores that are present in the system. Okay, so that's why we say when we talk about compressive strength versus W by C ratio, so this is the curve we form. So as the W by C ratio increases, the compressive strength decreases. Why? What is the reason? Due to the presence of more pores in the system at higher W by C ratio. Okay, so when there are more pores in the system, what will happen? They will provide a easier path for a moisture and aggressive ions to penetrate through the concrete. Okay, so that's why having a lower W by C ratio gives us a dense compact microstructure with fewer and smaller pores and more disconnected pores, and this significantly reduces the permeability and increases the durability of concrete. The second image shows how the size of aggregates affects the quality of concrete after hydration, okay, or during concreting. So in the top case, we are using similar size of aggregates. So when we are using a similar size of aggregate, what will happen? There will be pores in between aggregates. Okay, these will be like large voids between the aggregate particle, and they can result in higher porosity inside concrete, and that will reduce the durability of concrete. However, in the bottom image, you see there is a mix which is having different aggregate sizes. So this is one size of aggregate and this is one more size of aggregate. So what will happen, these smaller aggregates, they will try to fill the gap between the larger aggregates, and then they we have cement paste also. So in combination, all these three will lead to better packing density in my concrete. Okay, there will be more packing inside the concrete, there will be lower porosity or voids inside the concrete, which will improve the strength also and which will enhance the durability of concrete also. So this is the effect of packing density, or we can say different particle size present in the concrete. And this slide highlights how the use of supplementary cementitious material like fly ash, ground granulated blast furnace slag, and silica fume can influence the durability of concrete. So these materials, they are known as mineral admixture, and they are also referred as pozzolans. So okay, so what these pozzolans does, they are the class of siliceous and aluminous material that on their own have a very little or low no cementitious property. However, when these materials are finely divided and in the presence of moisture and having calcium hydroxide source nearby, they can react with they can react to form similar hydration properties that we observe in a normal OPC system. Okay, so you can see these reactions that are here. So this reactive silica and alumina, these are coming from my mineral admixtures. Okay, or what we'd say pozzolans. Okay, and this CH is something which is coming from OPC. So when we talked about hydration of OPC, we talked about silicate hydration, C3S and C2S hydration. In this, we saw there are two things that is produced: CSH is produced and CH is produced. And we said that CH is a waste thing. We don't need CH in my system because CSH is the thing which is contributing to the strength. So what these pozzolans are doing, they are consuming this waste CH that is produced by the OPC to convert it into calcium silica hydrates or calcium alumino hydrate. Okay, which is the primary strength giving compound in concrete. So this is known as pozzolanic reaction. These two reactions that you see here, these are the pozzolanic reactions, and this is the use of mineral admixture. Okay, so that's why we say these are additional additions to a concreting system that is done to enhance the property of concrete. Okay, now when these materials react with CH, which is a byproduct of cement hydration, they are converting into a CSH, which is a primary strength gaining compound. So they are improving the durability of concrete by reducing the lime, by consuming the lime that is there in the concrete. As at the same time, since they are forming some hydration products, they are contributing to refining the pores of the concrete and strengthening the interfacial transition zone also, making concrete denser and less permeable. Okay, so they are refining the pores, they are refining the interface, which is giving high strength and durability. uh, these reactions occur sometimes these reactions are mainly have a slow rate of reaction. Okay, they have a slow reaction rate because they depend upon the CH that is released by the by the C3S and C2S from OPC, and then this CH is what is consumed by these pozzolanic materials. Okay, so that's why they have a slower rate of reaction and they have a low heat of hydration. So in that way, they don't cause any durability issues in terms of cracking. And if we need to accelerate this, we can accelerate by addition of alkalis and gypsum. So this is like beyond the scope of this course. So this you can just uh, remember. The key point here is these three: lime consuming, pore refining, and interface refining. At the same time, it has a lower heat of hydration. So in this way, they can improve the durability of concrete by forming more dense microstructure of concrete. And this slide presents various types of chemical admixture that is used in concrete for performance enhancement and durability enhancement. So retarders, we know they delay the setting time, or they delay the setting time, which helps us to maintain a workable concrete mix for a longer time. okay, which can avoid issues of honeycombing or poor workmanship on site. Then there is accelerator, which does the opposite. They speed up the setting and which is needed, especially in cold weather concreting, where the we need faster strength gain, or in cases where we need a faster strength gain and early strength gain, we use accelerators. Okay. Then they shrinkage reducing agents which minimize cracking that can occur due to shrinkage issues. There are superplasticizer which improve the flowability of concrete, so that there is less chances of honeycombing in concrete if we are pumping the concrete. There are air entraining agents which resist the freeze and thaw effect in concrete. So when we'll talk about freeze and thaw, we'll see why we need pores inside concrete in cold climatic condition. And finally, there is corrosion inhibitor, which forms a like kind of a protective layer over the steel surface, which protects the steel from aggressive ions and increases the durability of concrete. So these are some of the ways in which chemical admixtures also contribute in enhancing the durability of concrete. So all in all, we can say each admixture plays a vital role in extending the service life of concrete, and their choice of admixture will depend upon the condition, the aggressiveness of the environment, or the quality of concrete that we want to produce. Okay, just try to answer these two questions. Anna, today he has class. I don't know the timing. Okay, for question number 9, yes, the correct answer is B. Okay, what is the primary environmental benefit of using mineral admixture? It reduces the CO2 emissions by replacing Portland cement. So we saw in the production of Portland cement that there is CO2 emission due to burning of fuel also, and due to burning of limestone that converts into CaO and releases CO2. So if we are using less OPC and we are replacing it by supplementary cementitious materials like mineral admixtures, we will reduce the CO2 emission also. Question number 10. Yes, the correct answer is false. Pozzolanic reaction doesn't occur immediately after mixing of concrete. It is a slower secondary reaction that begins after initial hydration of cement. So, after initial hydration of cement, CH is released by OPC, and that released CH is what is consumed by mineral admixture to form additional CSH. So that thing you can see here in this graph. Okay, I have just shown one illustration. So this first curve, the blue curve, shows the strength gain in OPC that is happening. Okay, when we add, when I will replace small part of OPC with fly ash, you will see initially the strength gain is smaller. Why? Because some CSH is not, it is not like some OPC we have reduced, so CSH formation has been reduced initially, but slowly as CH will convert into CSH, the strength gain will increase, and so that's why you see after 28 days the strength is more in OPC plus flash system rather than in OPC system. And the second figure here shows this same explanation. So in B, this B represents this OPC, okay, and A represents OPC plus fly ash. So in this you can see initially in pure OPC system, CH will be released. It is not consuming, it is just getting released and it will reach a plateau. However, in OPC plus fly ash system, as the CH is released, it is getting consumed by the fly ash to form CSH. So that's why it will first increase, and then it will reduce as it is getting consumed by supplementary cementitious materials. Okay, so that's why we say it has a slower strength gain because it depends upon the release of CH. Clear with these two questions? If yes, try to answer these three questions. So these three questions are based on chemical admixtures. Okay, the previous two were based on mineral admixtures. Any doubt? Okay, so for question number 11, the effectiveness of shrinkage reducing admixtures can be reduced when it is used in conjunction with. So the correct answer is air entraining agents. So what happens? They both of these agents they can interfere with each other. Shrinkage reducing admixture may reduce the stability or the quality of quantity of entrained air, which can affect the freeze thaw resistance and which can affect the performance of a air entraining agent. Okay, they are functioning in a different way. Okay, so that's why these two reagents are not used together. They can affect each other's performance. Okay, air entraining agent is like a very different type of chemical admixture that we are using. Here we are increasing the porosity rather than reducing. And in shrinkage reducing admixture, we want our concrete to be compact. We don't want our compact to be much porous. Okay, so that's why they can't be used together. Which admixture type is particularly sensitive to temperature variation during concrete mixing and placement? Okay, so the correct answer for this is D. Why? So when we talk about accelerators, they are highly temperature sensitive. Their effectiveness increases at high temperature and their effectiveness decreases at lower temperature. Why? Because in accelerator we are accelerating the chemical reaction. When we are accelerating the chemical reaction, more heat will be generated. So higher temperature will suit them. However, in lower temperature, they want to accelerate the reaction, but the environment is cold. So that will become a barrier for them, and they won't be able to significantly impact setting time or early strength gain in lower temperature. Okay, so that's why we say accelerators are sensitive to temperature variation. Question number 13, has anyone answered? So, in context of corrosion inhibition of concrete, I should write reinforced concrete here. Which mechanism most accurately describe how corrosion inhibitor function? Okay, so when we are talking about corrosion inhibitor, these are also used as an admixture. We are admixing them in concrete while we are pouring concrete. Okay, so what happens, these inhibitors, they will first diffuse in from inside concrete to the reinforcement surface, and as I described earlier, they form a protective film on the reinforcement. Okay, so that's why the correct answer will be they diffuse through concrete pores and deposit on the steel surface to form a protective film. Okay, all these are admixtures, so they are used as initially during concreting. Okay, any doubts in this part? Okay, so let's move ahead.
No, sir, no.
Now we'll start with the chemical attacks. Okay, so let's start with sulfate attack. So sulfate attack basically is the reaction between sulfate ions and the hydrated cement paste. Okay, so it is the reaction between sulfate ion and hydrated cement paste product. Okay, so there can be two forms of sulfate attack. There is external sulfate attack and there is internal sulfate attack. So external sulfate attacks means the sulfate ions are ingressing into concrete from external environment. The external environment can be groundwater or seawater, or due to some bacterial action in sewer lines. So from these, sulfate ions are ingressing into the concrete and causing degradation of concrete. That comes into external sulfate attack. Internal sulfate attack means there is a release of sulfates inside concrete that has taken place. And in this case, there is formation of attringite that occurs after concrete has hardened, and we say it as delayed attringite formation. This will see in couple of slides how this is causing a problem. Okay, so just understand one difference here. External sulfate attack means sulfate ions are moving inside concrete from environment, which is causing degradation of concrete. And internal sulfate attack means there is a late release of sulfate ions inside concrete, which is causing degradation problem. Okay, now what is the end result of this? So sulfate attack, what they does, they cause softening and loss of integrity of concrete, due to which there is cracking in concrete, and due to which there is durability issues in concrete. So to tackle this, to limit this sulfate degradation, IS 456 says that the total soluble sulfate content in concrete mix should not be more than 4% by the mass of cement. Okay, and aggregates should not contain more than 5.5% of sulfate. Okay, so to tackle this degradation due to sulfate, the various limits has been imposed by Indian standard. Okay, now how sulfate attack occurs? So basically, each individual hydration product can give rise to a new compound because of sulfate attack. Okay, now the primary products that result from sulfate attack, it is gypsum and ettringite. Okay, so in the first reaction you can see CH is reacting with sulfates to form gypsum. Okay, and in the second and the third reaction you can see this ettringite formation is occurring when sulfate reacts with monosulfates and C3A. So you can see these are sulfates. Okay, it is reacting with monosulfates and calcium aluminates to form ettringite. Okay, now if you see in the second and the third reaction, the reaction consumes a lot of water. Okay, 20 moles and 32 moles of water. And due to this consumption of water, there is swelling in the hydration products that are forming. Okay, and this leads to high surface area of the hydration products of which in this case is ettringite, which leads to cracking and disintegration in concrete. Okay, so this is the reason how sulfate attack is causing problem in concrete, due to swelling of the hydration product. Okay, so here you see sulfate ions, they are reacting with monosulfates and calcium aluminates to form a ettringite, which is consuming a lot of water and causing forming a hydration product which is having high surface area, and accommodating this high surface area products inside concrete can give rise to cracking and disintegration. Okay, now there can be other reactions also which can happen. So here we have talked about calcium sulfate as a source. There can be other sources of sulfates also. There is magnesium sulfates also. Okay, so magnesium sulfate, they primarily damage the CSH gel. Okay, so what happens? Magnesium sulfate, they react with CSH to form gypsum and serpentine. Okay, and this serpentine has a poorly crystalline material, and it collapses the structure of CSH. Okay, so it is not just one source of sulfate. There can be different salts of surface which can attack concrete in different ways. Okay, so this was external sulfate attack. How sulfates from atmosphere is causing problem due to swelling. Okay, they are causing swelling issues in concrete, which is causing degradation in concrete. Now, when we talk about internal sulfate attack, there is a thing that is known as delayed ettringite formation, or we can simply say It means formation of ettringite in concrete at a later ages after initial curing period. Now, when such condition will arise, so it occurs in concrete that has experienced higher elevated early temperature. So at initial time during curing, okay, if there is high early temperature, okay, which can be imposed due to heat treatment or significant internal heating or due to a moisture, what happens in this high early temperature, the formation of ettringite is not happening initially. Okay, so initially we have gypsum in the system. Okay, this reaction between gypsum and C3A, it won't happen. Okay, if the temperature is very high initially. Now there is sulfate that is present in the pore liquid, okay, for a usually long period because it is not consumed initially. However, at later ages, once the concrete has hardened, this temperature will reduce, and then sulfate will start reacting with calcium and aluminate phases to form ettringite. And this delayed reaction of sulfate and calcium aluminate phases, they give rise to expansive pressure because ettringite have higher surface area and it causes cracking in concrete. Okay, and this process is known as delayed attringite formation. Okay, so here this elevated early temperature was the important thing which has given rise to delayed attringite formation. Okay, so attringite is forming as at a later ages than initial age, and that attringite has a higher volume compared to normal these initial products. And this higher volume, if they will form at hardened concrete, they can cause cracking issues in concrete. Okay, this is delayed attringite formation. Now this effect of sulfate we can see in the image. Okay, in the first image you can see the cement paste interface where attringite lining is present. Okay, and it has led to 2.8% expansion. In the second image you can see how submerged column is experiencing bulging here and here due to sulfate attack. And how to prevent this? We can prevent by using sulfate resisting cement which has low C3 content. So if there is low C3 content, there will be less amount of ettringite formation, and there will be less amount of sulfate attack happening. We can use SCMs which can consume CH and create a dense microstructure which will lower the ingress of sulfate ions. We can make concrete impermeable, which is what SCMs is doing, or we can reduce the W by C ratio also to make concrete impermeable, and this can be some of the preventive measures for sulfate attack. Okay, everyone is clear with the sulfate attack part? Any doubts in sulfate attack? Okay, so after sulfate attack, we have alkali silica reaction. So, what is this? So, here I should write as an alkali silica reaction. Okay, so here it is the reaction between alkalis with a certain type of aggregates. Okay, so alkalis are coming from cement and chemical and mineral admixtures, and maybe coming from impurities in aggregate and water, and silica is coming from aggregates. So generally we want aggregates to be inert. However, if our aggregates are amorphous in nature, what will happen? They will have some reactive silica, and this reactive silica from aggregate can react with the alkalis that is present in the cement system to give rise to alkali silica reaction. Okay, so if we simply write what is this alkali silica reaction, so alkali ions like sodium and potassium, in the presence of reactive silica and moisture, they form alkali silica gel. Okay, which is expansive in nature, and this expansive product in concrete can cause cracking in concrete. So in both the systems there is a similar thing, there is the expansive product formation. So when we talk about a hardened concrete system, we talk about a dense microstructure which has a very small porosity or very small gap. Okay, porosity is generally like 5 to 10% porosity is there in the system. Okay, now in this dense microstructure, when there is formation of some expansive product, what will happen? They will generate tensile stresses inside the concrete, and that tensile stress, if it is more than the strength of the concrete, they can lead to cracking in concrete. So that's why we don't want expansive products in a hardened concrete system. Now, how this alkali silica reaction is occurring, that I have tried to explain in this 5-step process. So first we have amorphous silica in aggregates, and during cement hydration there is release of alkali ions in the pore solution. Okay, so step 1 is release of alkali ions from cement hydration. You can see alkali ions here they are getting released from the cement hydration, and we have a amorphous silica that is there in aggregate. Now, in the presence of alkaline medium, the silica in aggregates they break down due to hydrolysis. Okay, so you see this SiOH, it is breaking down in the presence of alkaline medium into SiO minus and H2O ion. Okay, H2O molecule. Now, this is known as silanol groups. Okay, these are silanol groups. Okay, so sorry, I should have mentioned here. Okay, so in the presence of moisture, this reactive silicate is breaking down into SiOH groups. Okay, so these are silanol groups. Okay, now these silanol groups in the presence of alkaline medium, it breaks down into SiO minus and H2O. This is step 3. Okay, step 2 was initial hydrolysis of siliceous fraction in highly alkaline solution, and step 3 is this silanol groups, they are breaking down into SiO minus. Okay, once these groups are broken down into SiO minus, they attract the alkali ions from the pore solution. So this SiO minus, they are attracting the alkali ions from the pore solution, and they are forming a gel around the aggregate. Okay, and this formation of gel causes imbibition of moisture. So they are attracting moisture and they are swelling, and this swelling of uh, the aggregate surface due to alkali silica reaction gives rise to forces, tensile forces inside concrete, which leads to cracking inside concrete. Okay, so this is the process. So we have this reactive silica which is converting into silanol groups in the presence of moisture. In the presence of high alkaline medium, the silanol groups are breaking down into SiO minus. Okay, this SiO minus, they attracts alkali ions due to charge difference, and these they form a gel over the concrete surface which absorbs water, which is known as imbibition of water, we can also say, and they generate tensile forces, okay, due to swelling. And this expansive forces or expansive gel, the forces that this generates, it causes cracking in concrete. Okay, so this degradation generally appears in the form of map cracking. You can see like a map, cracks will appear on the surface of concrete. Here and here you can see how cracks are coming. So this is the effect of alkali silica reaction. And you can see in this image how gel formation is occurring at the aggregate surface. So you can see this aggregate and this gel that is present. Okay, and this gel is generating cracking. Okay, so similar to alkali, say there is alkali carbonate reactions also, where reactive carbonates in certain aggregates, they in the presence of alkali they form expansive products like magnesium hydroxide, which can cause cracking. And how we can prevent this alkali aggregate reaction or alkali silica reaction? By using non-reactive aggregates, or by using low alkali cements like SCMs, or by preventing water permeation by applying suitable coatings on the surface. Okay, so all this reaction requires water. Okay, so if we can reduce the ingress of moisture, then also we can delay or we can prevent the alkali silica reaction from occurring. Any doubts in these two processes, sulfate attack and alkali silica reaction? If you have any doubts, just post it in the chat box or try to unmute and speak so that we can have an interactive session. And if there are no doubts, if there are no doubts, just simply answer the questions that I'm asking, because those questions are framed based on what I'm explaining only. Okay. Okay, for question number 14, which environmental condition accelerates both external and internal sulfate attack? So the correct answer will be yes, B is the correct answer. Alternate wetting and drying cycles in sulfate rich water. So what happens when we have alternate cycle? It is like repeated exposure to sulfate ions also. And now in wetting drying cycles, the ions are like due to moisture difference. The moisture is also moving inside, and due to sulfate exposure, the sulfate ions are also moving inside. So both moisture and sulfates are moving to greater depth, both are getting forced. Okay, so that's why it accelerates both external and internal sulfate attack. And internal, why internal? Because sulfates will be present internally at different spots for a more time in drying period. Okay, so it should not say here external, we can just write it as external sulfate attack, because internal sulfate attack is mostly dependent upon the initial curing temperature. Okay, so correct question will be which environmental condition accelerates external sulfate attack the most. For internal, high temperature curing is the thing that will accelerate the internal sulfate attack. Question number 15. So here you have a graph. Okay, there are three different types of cement, and based on if I fix a W by C ratio, suppose at point 0.6 W by C ratio, there are different expansion percentage you can see in this cement. Okay, so you need to tell me which curve represent which type of cement is for this first curve, which type of cement is for second curve, and which type of cement is for third curve. Okay, and in all the three types of cement that I have mentioned here, I have mentioned what is the C3 content. Okay, so we know if there is higher C3 content, there is more chances of sulfate attack. Okay, so what will be the curve one? Which type of cement represents curve one? For 15, there is no option. You need to tell me this curve one. What cement type is present in this concrete, which is presented by curve one? Okay, so if there is higher C3 content, there will be more sulfate attack chances, so there will be higher expansion. So this curve 1 will represent type 1 cement. Okay, now in type 2 cement, there is lower C3 content, and type 5 cement, there is much lower C3 content. So this means that this curve 2 will represent type 2 cement, and this curve 3 will represent type 5 cement. So lower is the C3 content, lesser will be the chance of sulfate attack to occur, and lesser will be the expansion. Okay, expansion is due to ettringite formation, which will swell in the presence of moisture. Okay, so that expansion will be less where the ettringite formation will be lower, and ettringite formation will be lower where C3 will be less. Okay, now question number 16, which of the following strategies reduces the risk of alkali silica reaction in concrete? So what we can do to reduce alkali silica reaction in concrete? Any?
C.
Yes, the correct option is C. So if we use low alkali cement, what will happen? Even if we have a high reactive aggregates, if there is alkali presence are low, then the alkali silica reaction chances will be lower. And the better thing is to use a pozzolanic material. So what will happen? Pozzolanic material, they will densify the concrete, and they will reduce the moisture ingress in concrete. We saw in the alkali silica reaction flowchart that moisture is also important step in that reaction. So if we have a dense concrete, then also we can reduce the risk of alkali silica reaction in concrete. Now try to answer these three questions more. Question number 17, 18, and 19. So what will be the answer for question number 17? Which of the following best explains the degradation mechanism in thomsite sulfate attack? So this is like the second, due to magnesium sulf due to magnesium sulfate that we saw, no, that category. Okay, so that is, we saw, for this we saw what explanation? So for this we saw it is the CSH that is affected. So CHS is getting converted into a weaker calcium silicate system, which leads to complete loss of cohesion and the strength of the concrete. Okay, so when CHS degrades, there is loss in strength of concrete that is happening. Now, question number 18. You using a locally available aggregate for a project. The petrographic analysis reveals it has reactive silica in it. So, what is the most effective long-term strategy that you should use without replacing the aggregates? So, which strategy you can use? So, for 18, the correct answer will be A. So, if we will use a supplementary cementitious material as a replacement of OPC, we can consume alkalis, and we can reduce the pore solution alkalinity, and we can refine the pore structure also, which can help us to reduce the alkali silica reaction chances in concrete. Okay, third question, for a reactive concrete mix, for a concrete mix having reactive aggregates, which of the strategy reduces the risk of alkali silica reaction? Which strategy minimally reduce? So which among this, which will be the least effective? Okay, so this is just a repeat of question number 18. If you will see, using OPC with fly ash, it will densify the pores, it will reduce the risk of alkali silica reaction. If we have OPC with low alkali content, then again we can reduce the risk of alkali silica reaction. And sometimes we're introducing lithium nitrate also helps in reducing the chances of alkali silica reaction in the system. Okay, the one thing that will least contribute is the control of RH. Okay, because over a long period of time, this is not a reliable solution. Okay, so that's why the minimum effect or minimum effectiveness will be given by the maintenance of RH during curing. Because when we talk about these reactions, they are long term reaction, they can happen at later ages also. And for long term processes, maintenance of just RH during curing is not a solution. Okay, we need solutions which are long term. Any doubts in these three questions?
No, sir.
Okay, so let's move ahead to the final part of this chemical degradation, that is freeze and thaw reaction. Now, what are the critical points here that we need to take care while understanding freeze and thaw? One thing is water expands by 9 to 10% upon freezing. So, when water converts into ice, there is an expansion of 9 to 10%. The freezing point of small pores is depressed by a larger extent. So when we talk about small pores and big pores, okay, the freezing point of small pores are much lower. So suppose water in big pore is freezing at 0 degree Celsius, the same water in small pores will freeze at minus 20 degrees Celsius. Okay, so that is one point you need to remember. And if concrete remains frozen for throughout its lifetime, it is not much of a problem. However, deterioration occurs only when there is successive cycles of freezing and thawing. Okay, so frozen water in concrete is not a problem. It is just freezing, then again ice, then conversion to water, then conversion to ice. That is the problem which causes deterioration in concrete. Okay, now how this is occurring and why we are saying freezing and thawing is a problem. So what happens, freezing of water starts in capillary pores. So we have seen larger pores, they freeze earlier than smaller pores. So the water in capillary pores, they will freeze. Now what will happen, due to this, ice formation will start. And as ice formation will start, this unfrozen water, they will experience some hydraulic pressure due to the formation of volumetric ice, expansive ice. So this ice formation, it will occur. What will happen, due to this, the water will experience hydraulic pressure. They will start to move inside the pore system. So water will start to travel through the paste, and this movement of water inside the paste will generate stresses. Okay, if the longer is the path of flow of water, the more pressure the water will generate. And this pressure, if it exceeds the cement strength, it will cause failure in the concrete, if it is more than the concrete strength. Okay, so what is happening, pressure is generating, pressure is releasing, pressure is generating, pressure is releasing. And in this way, over a successive cycles, it will cause fatigue in this concrete system, and this will cause cracking in concrete, and it will lead to degradation of concrete. Now, in such cases, that's why we have air entraining agents. So what air entraining agent does, they deliberately add voids inside the concrete. Now when this water is moving inside the concrete, okay, due to formation of ice, if that has a void, it will be able to release its pressure that is getting generated due to water movement. And that's how air entraining agent, they remit the freeze and thaw problem inside concrete. Okay, they provide a relief station for water movement. Okay, so here you can see some of the examples what is happening due to freeze and thaw attack, or we say frost action. So in the first image you can see how this frost action is causing rock to crack. So initially water was collected. Okay, now water freeze and it expands, which causes crack in concrete in this rock. Now as as the ice will melt, the water will deliberately penetrate to deeper depth. Then again it freezes, it expands, it causes crack to further propagate inside. And in this way water goes deeper and deeper inside this rock, and finally at one point it will crack the rock. Okay, so it is freeze thaw effect that is happening, which is causing the cracking. And the second image, you can see the pavement settlement that is happening due to freeze thaw action. So water penetrates inside. As temperature drops, water freezes and expands, which causes cracking. And this cracking leads to further degradation of the pavement and further cracking in the system, uh, or problems in the performance. And in this third image, you can see this action of frost, freeze and thaw, how it is appearing on the concrete surface. So complete disintegration of cover concrete is happening due to this freeze thaw effect in these columns. Okay. Now, how we can prevent, by using air entraining admixtures. So you see, they create well-distributed air voids in the system, which act as a relief point, or we can use a low water to cement ratio concrete. So what this will does, that it will decrease the porosity in concrete. So we saw if there are smaller pores, the freezing won't happen at higher temperatures. So very small pores makes freezing difficult, and if freezing is difficult, this freezing and thawing effect will be reduced. Okay. Any doubt in this part, in freeze and thaw reaction part? Okay, so let's move to the next segment. So next segment of degradation is corrosion in reinforcement steel. Now, first of all, before understanding what corrosion is doing, we need to understand that corrosion is a natural phenomena. This will occur. We can't stop corrosion from happening. Why? Because initially in the ores, we have iron ore like hematite, magnetite. Iron is present in the form of oxide. Now, when we make steel, we process this ore into steel, which is Fe. So, we are giving energy to the system. We are increasing the energy state of the system. But what law of nature says? Every metal or every material is stable in its lowest energy state. So, what will happen? This metal, it will start try to convert back to its lower energy state, which is this ore state. And this process, this second process that you see here, this is what is known as corrosion. Okay, so it is a natural phenomena, we can't stop. Okay, we can control it, we can delay it, but we can't prevent corrosion from happening. However, when we talk about a reinforced concrete system, the pore solution or the porous matrix in concrete is rich in alkali ions. Okay, like NaOH, sodium hydroxide, potassium hydroxide, and calcium hydroxide. These are rich in pore solutions of concrete or in the pore spaces of concrete, which causes high pH in concrete. And when there's high pH in concrete, there's one mechanism that occurs which is known as passivation of reinforcement steel. So what happens when the steel rebar are present in high pH environment? There is a protective film that is formed over the steel rebar, and thus this film is known as passive film. And this passive film, it shields from further corrosion from happening. Okay, so this reduces the rate of corrosion. The natural corrosion, at the rate at which this natural reaction is occurring, it will be reduced due to this presence of passive fill. However, in reality, what happens? There are aggressive ions that are present in the surrounding. Once these aggressive ions move through the concrete cover and reach the steel reinforcement, they can break this passive layer and they can increase the rate of corrosion. And what are these aggressive ions? These are carbonation and chlorides. So that's why we have two types of corrosion in concrete: carbonation induced corrosion, chloride induced corrosion. So what these two are doing? They are destabilizing this passive layer, or they are breaking this passive layer, which is increasing the rate of corrosion in concrete. Okay, corrosion was meant to occur, but due to passive layer, it was occurring at a very small, slow rate. But once the passive layer will break, it will again occur at a faster rate. Okay, so what's the end result of corrosion? It is the corrosion products. Okay, and these products can be of different composition based on the availability of moisture and the oxygen in the environment. Okay, you can see some of these products. That can be iron hydroxide, magnetite, hematite, iron 3 hydroxide, goethite, ferroxide. Okay, there can be different products that can form when steel reacts with the environment. Okay, and these products, all these have a higher volume. They have they occupy more volume than the original steel. Okay, now inside concrete, as we saw with sulfate attack and other attacks also, if there's high volumetric material which is present inside a dense concrete, it can lead to tensile stresses in concrete, and if these stresses exceeds the strength, they can cause cracking in the concrete. So the same thing is happening here, and you can see these happening in different images here. So you can see this main reinforcement corrosion, stirrups corrosion, and due to this, cracking happened, and there's cover spalling and delamination that has happened. In this bridge deck, you can see there's corrosion which has led to exposed reinforcement from inside due to cover spalling. Here you can see on these walls, reinforcement are getting exposed due to cover spalling, which has happened due to corrosion. And here you can see in these steel structures also, due to corrosion, the steel is getting consumed and it is weakening the structure. Okay, and this image shows what is happening. Okay, so this is spalling of cover. Complete cover has been chipped off from here, and this is known as delamination. So my concrete and steel, I have lost the bond. That loss of bond is known as delamination of the cover concrete, and this is happening because of formation of expansive rust product inside concrete due to interaction of concrete with the environment as the passive layer breaks. Now, this degradation due to corrosion, due to aggressive ion, it happens due to two reasons: direct effect and indirect effect. So, the chloride induced corrosion causes direct effect on steel. Okay, and carbonation induced corrosion causes indirect effect on steel. Okay, how? So, when steel itself gets affected due to aggressive ions, we say it is a direct effect. So what happens? These chloride ions, they ingress through the cover concrete, they reach the passive layer, they depassivate the passive layer, and they react with the iron to form soluble compounds. Okay, that's why we say it has a direct effect on steel. Okay, it is not disturbing the concrete, but it is directly affecting the steel reinforcement. And by indirect effect, we mean when the concrete is affected because of aggressive ions, which causes depassivation of steel, and that is done by carbonation. So in carbonation, what happens? CO2 from atmosphere in the presence of moisture, it reacts with the calcium hydroxide that is present in the pore system to form CaCO3. Now, we know we need high pH environment inside concrete for passivation to occur. If CH will be consumed, the pH of the concrete will reduce. If the pH of concrete will reduce, what will happen? My passive layer, which formed over the steel surface, it will collapse. And if my passive layer will collapse, oxygen, moisture from environment can interact with the steel and increase the corrosion rate. So that is carbonation induced corrosion. So it is not directly affecting the steel, but it is affecting the concrete, which is affecting the steel. Okay, so that's why we say it is indirect way of corrosion. Okay, any doubt in this part related to corrosion? What do you mean by passive layer? What is happening when corrosion is happening? What are the corrosion products? How they are causing cracking in concrete, and how chloride and carbo CO2 causes corrosion inside concrete.
No, sir.
You have any doubt? Is this part clear to everyone? So this topic corrosion itself is a very big topic. Like I have separate sessions that I have uploaded on my NPTEL channel. If any one of you wants to go deep into how this is happening, what is the electrochemistry behind reactions, what are different reactions, how they are getting affected by different reasons, you can just visit some of my lectures. Here I've kept it very small because we have a lot more things to discuss in this session. So this is a very crisp way to explain corrosion. Okay, my research area is also related to corrosion of reinforcement steel. So if you have any doubt in this part, you can ask me freely.
Okay, sir. Now is clear.
Okay, just try to answer these questions. So the things that I have not covered in the theory, I will try to address through questions so that the corrosion thing is clearer to you. Okay, so just quickly try to answer these questions. Okay. Let me answer the question number 20. Which electrochemical reaction occurs at anode? Okay, so I will just give you a basis behind this. So when we talk about corrosion, there are two reactions. There is anodic reaction and there is cathodic reaction. Okay, so anodic reaction is oxidation and cathodic reaction is reduction. So oxidation is happening. We saw iron ore. Iron is present in Fe2 plus and Fe3 plus. When we convert it into metal or steel, it converts into Fe. Now it will try to convert it back into Fe2 plus and Fe3 plus. So this is oxidation reaction. So at anode, what happens? Fe is converting back into Fe2 plus. Okay, so this is known as anodic reaction. Now it will release some electrons. Now I need these electrons to be consumed for this reaction to continuously move forward, and that is done by the reduction reaction. So oxygen and moisture from atmosphere, they consume these ions to form hydroxide ions. Okay, and finally this ferrous ion and hydroxide ion, they combine to form ferric iron oxides and hydroxides that we saw in this slide, which are the corrosion products which are expansive in nature. So this is the net corrosion reaction that is happening. So for question number 20, which reaction occurs at anode, so the correct answer will be C. Iron oxidation is something which is occurring at anode. Now, question number 21. Corrosion induced cracking in reinforced concrete typically follows. So, what is the pattern of crack that we see in corrosion? I hope everyone are clear with this anodic and cathodic reaction. So, very simply, I have tried to explain what is happening, what is anode and what is cathode. Okay. Just remember, corrosion is a natural process. It is bound to occur. And in nature, iron is present in its Fe2 plus and Fe3 plus state. So, it will try to convert back to that state. Okay. That's why we say it is an anodic reaction. Fe to Fe2 plus conversion. It is oxidation. Okay, so 21, the answer will be C. Okay, so when we talk about corrosion, the cracking, it is a longitudinal crack that occurs along the reinforcement length. Okay, so in all these cases, if you see, there are longitudinal cracks that are generated. Like in this image, you can see there were longitudinal cracking that generated that led to spalling and delamination. The same thing you can see here also. It is a longitudinal crack that is generating. Okay. Try to answer question number 22. It is related to carbonation induced corrosion. And 23 also is related to carbonation corrosion. So remember the reaction that I told here. I will just copy this part. Okay, this part you just remember how CO2 is reacting, what it is doing to the system. Now, based on this, try to answer these two questions. Can anyone tell me the answer for question number 22? What is the typical critical pH threshold at which passive layer of steel reinforcement become unstable? Okay, yes, the correct answer is C. So when pH of concrete, it is initially usually in the range of 12 to 30. Now due to carbonation, what is happening? CH is getting consumed. So pH will reduce from 12. Now when this pH comes below 9, what happens? The passive layer becomes unstable. It will break, and that will lead to corrosion, commencement of corrosion at the reinforcement. Okay. Now, which environmental condition leads to fastest carbonation in concrete? No, for 22 it is C. For 23, can anyone tell me the answer? No, C is not the right answer. Okay, so let me tell you what is happening. This reaction that you see here, it is a two-part reaction. I have written the final reaction. Okay, so what happens during carbonation? Initially, CO2, it reacts with water to form H2CO3. Okay, now this H2CO3, it reacts with calcium hydroxide in the system to form CaCO3 plus water. Now, we know in this reaction two ions are important, CO2 and moisture. So this is gas, this is liquid. Now, what will happen if I have very low RH? Okay. In low RH system, what will happen? There will be no moisture in the system. So this first reaction won't occur. So carbonation rate will be very slow. However, if I have a very high RH system, like RH of above 90%, like 100% relative humidity, what will happen? There is a lot of moisture in the system, but diffusion of CO2 through moisture is very low. Okay, CO2 is a gas. It needs air voids to diffuse through concrete. If all the voids are filled with water, the CO2 won't be able to diffuse, penetrate much deep inside concrete. So that's why there will be less amount of CO2 in the concrete, and then again this reaction will be slower. So that's why we need a moderate humidity, okay, to accelerate the carbonation the fastest. Okay, and this you can see here. Okay, carbonation rate versus relative humidity graph. Okay, so at lower relative humidity, carbonation rate is small. At high relative humidity, it is small, but in this range of 50 to 70 or 60 to 80, it is maximum. Okay, there are enough water in the system for carbonic acid to form, and there are enough air voids in the system for CO2 to penetrate. Okay, and this is a test that is used for carbonation, phenolphthalein indicator. So phenolphthalein, what happens when the pH is above 12? Okay, when the pH is above 9, it shows pink color, and when the pH is lower than 9, it shows a colorless appearance. So we spray this phenolphthalein indicator and we see what color is coming. So here, this is the carbonation depth, and in this is the carbonation depth. So in this way, we can predict up till what depth pH of concrete has been decreased below 9. Okay, so this test we use for carbonation. Now try to answer these three questions. These are related to chloride induced corrosion. If you have any doubts in the discussion that we are having, just ask freely. Okay, for anyone, can anyone tell me the answer for question number 24? Which type of corrosion is most associated with chloride ions? So we saw chloride ions, they are breaking the passive layer. Okay, and then they are accelerating the corrosion. Okay, so in such cases, it is like chlorides will move through the pore structure of concrete. Now, and it will depend upon the connectivity of pores also. So the places where the pores are connected deep inside the concrete, their chloride ingress will be fast. Okay, and the place where chloride has reached the steel reinforcement, only that place it will break the passive layer. It won't uniformly break the passive layer. So that's why we say it is a localized steel loss that happens when chloride moves through the reinforced concrete. And that type of corrosion is known as pitting corrosion. So at a particular spot where chlorides have broken the passive layer, there only the corrosion will accelerate. Okay, that will form a weak link for corrosion to occur. While in case of carbonation, it is the uniform loss in pH of the cover that is happening. So the corrosion that happens, it has a uniform corrosion. We say that is happening over the entire steel surface. Okay, so in chloride induced corrosion, it is pitting corrosion or localized corrosion, while in carbonation, it is uniform corrosion. Now, which type of cement is most effective in reducing the chloride penetration in reinforced concrete? Can anyone tell me the answer? Okay, yes, the correct answer is C. So when we use a Portland pozzolana cement, which has like 15 to 35 percentage of fly ash in it, what is happening? We are giving rise to secondary cementitious reaction that is happening, which will cause pore densification, which will reduce the porosity. If the porosity is reduced, the chloride penetration will reduce, and then it will reduce the rate of corrosion. Why does the combined effect of carbonation and chloride attack significantly accelerates reinforcement corrosion? Can anyone tell me what is happening? So what does carbonation do and what does chloride do? So if you know both the things, the answer is very clear. What will be the answer for question number 26? Okay. Yes, the correct answer is B. So carbonation reduces the pH of concrete. Now we saw when the pH of concrete is reduced, the passive layer destabilizes. And if it destabilizes the passive layer, what will happen? There will be less chlorides that will be needed to break the remaining passive layer. Okay, so it will accelerate the corrosion. Okay, it will ease the chlorides to break the passive layer. Okay, there is a thing which is known as chloride threshold. So when chlorides are reaching the interface, when they are accumulated in a certain amount, then only they break the passive layer. Okay, if my passive layer is thin, I will require less amount of chlorides at the interface to break the passive layer. If my passive layer is thick, more chlorides will be required to break the passive layer. And due to carbonation, as the pH decreases, the thickness of passive layer also reduces, and that lowers the chloride threshold that is required to initiate the corrosion. Any doubts in this part?
No, sir.
Okay, so let's move ahead. Now, the final part in aggressiveness of environment is related to the mechanical degradation of concrete. And here we talked about three major degradation types. So this is a very easy part. So that's why I will quickly move through it. So first is abrasion of concrete. So abrasion refers to wearing away of concrete surface due to friction from solid particles. Okay, and this friction, solid particles, by solid particles I mean sand or gravel, and this mainly comes in high traffic area or high flow zone areas. Okay, so in water bodies, due to movement of finer particles over the concrete river decks, there can be abrasion that is happening. Or in high traffic area, due to movement of vehicle, the rubbing of wheels with the concrete pavement surface, that can also cause abrasion to occur. So it is caused by repetitive rubbing, rolling, sliding, and impact of particles. Okay, so you can see here the example. This is a clean surface. Okay, and this is due to abrasion damage. Okay, so there is wearing of surface that is damaged due to rubbing of particles. Okay, second is erosion damage. So erosion is much like abrasion only. It involves progressive loss of concrete material from the surface due to the action of water flowing over the surface. Okay, so this was scrubbing action that the moving water is generating in near the river bed. It gives rise to erosion damage in concrete. So you can see here, this is a river bed, and due to movement of water, you can see significant cracking and damage has occurred. Here also you can see in a pipeline on the surface how different damages has occurred due to erosion. Okay, so it is more related to like fluid motion and velocity of flow, where damage is occurring due to scrubbing action. Okay, and this slides illustrates the cavitation process, which is like a specific form of degradation for hydraulic concrete structure. So basically cavitation occurs when high water velocity water flows over the surface which is having irregularities on it, which creates low pressure zone on the surface. So you can see in this image, there's irregularity on the concrete surface in this form. Now there's high speed water which is moving. Now when this water interacts with this irregularity, it creates a zone of low pressure. And now in this zone of low pressure, what happens? Bubble formation is happening. Okay, these bubbles, they will move due to this high pressure to a lower downstream area, and they will collapse on the surface of concrete. And this collapse of bubbles, repetitive collapse of bubbles on the concrete surface, it generates forces on the surface which cause material loss from the surface. So you can see this here, and here also it is written, occurs in location where rapid development dissipation of air bubble occurs. Okay, so this bubbles is forming in high low pressure zone, and they are moving uh, in the high pressure zone, and they are collapsing on the concrete surface, which is giving rise to forces and which is cracking the concrete. So you can see here there's a issue of cavitation. Here you can see cavitation damage, and here also you can see cavitation damage due to high flowing water. Okay, and this occurs mainly in dams. Okay, in dams you will see this issue is a major concern. Okay, so just try to answer these three simple questions related to this part. Okay, very simple questions. So first question is, which of the following factor has the least influence on the abrasion resistance of concrete? Can anyone tell me the answer of for question number 27? Okay, yes, the correct answer is D. So, what type of curing compound we are using? It is not concerned with the wearing of concrete. Aggregate hardness, it will the harder the aggregate, lower will be the abrasion. If I have denser microstructure of cement, my surface will have higher strength, and that will reduce the abrasion. But type of curing compound used will have the least influence. During high velocity turbulent flow in hydraulic structure, cavitation damage is most likely to initiate at which area it initiates? Okay. So for question number 28, the correct answer is B. Okay. So the places where there is surface discontinuities and edges, we saw these are the places where low pressure zones are created, and in the low pressure zones air bubbles are formed, which eventually collapse in high pressure zones downstreams. Okay. So initiation happens in near edges and discontinuities. Erosion in concrete structure is most severe under which of the following condition? So can anyone tell me in which condition erosion will be severe? Okay, yes, the correct answer is B. So we saw erosion is more influenced by the velocity of flow. Okay, now in high velocity flow, if it has suspended silt and sand particles, so they will create some wearing action on the surface as they will rub across the surface of concrete bed, and that will give to severe erosion damage on the surface. Okay. So in this slide, you can see some of the results that has been shown. So as the compressive strength increases, the abrasion loss decreases. Okay. As the water to cement ratio increases, there are higher chances of abrasion loss that can happen. And as the hardness of aggregate increases, the abrasion loss decreases. Okay. So this was related to first question. Okay, now let's quickly move into the final segment of this session. So we will take around 15 minutes more to complete this part. And this final segment, we will understand how this durability is incorporated in design. So in modern design, what happens is that we know the location of the structure. Okay, so the location of the structure is known to us. Now, based on the location, we have standard categorization of exposure severity, or we can say aggressiveness of the environment. So like you can see in this table, environments are classified into different exposure zones, and for each exposure zone we have given some guidelines. So what type of environment will come under what exposure zone, that is known to us. Now we know where our structure is located. So based on these guidelines, we can decide what is the exposure zone of our structure. Now, in that exposure zone, we know which aggressive ion is dominating. So if we see, if I take a structure very near to sea water, I know chlorides ion are dominating. If I take a structure where there's high amount of sulfate in groundwater, then I will say sulfate ions are dominating. If I have a structure which is located in industrial region, then I will say CO2 is something which is dominating. In cold region, I will say freeze thaw is something which is dominating. So based on the aggressive ions which are present in the environment, I can choose a suitable service life model, which contains conditions on covered depth, binder type, and other durability parameter. Okay. Once I have said, now for these demands, I will initially cast concrete in lab and I will test their fresh property, hardened property, and durability property. So what happens? I know the aggressive ions that are present, and I have taken certain control over this different parameters, and I have prepared a trial concrete in lab, and I have tested them whether they are working properly or not. If they are working well, then I will commence to the construction and I will build the structure. Once the structure is built, I will again test the structure. Okay, if it passes, then it is okay. If it doesn't passes the durability criteria, then either we will reject the structure and we will ask for complete demolition of structure, or we will recommend some remedial actions, like do some coating or apply some corrosion inhibitor or do some maintenance to get the durability of structure restored. Okay, so this is how a durability design approach is followed. Okay, based on the aggressiveness of the environment, we decide which ions are dominating. Then we take precautionary measure on cover type, binder type, and other indexes. We test the concrete in lab for fresh properties, hardened properties. Once we know whether whatever decisions we have made for mixture design they are working well, we commence to the construction. And after construction, we check the structure again for quality of concreting done. If it is not good, we recommend either reject the structure or some repair. Okay. Now, when we talk about durability indexes, these are simply some simple testing method which can be performed in lab to judge the durability of concrete. So this slide shows some of this durability testings that we have. So there is oxidation permeability test which measures the resistance to carbonation or ingress of air through concrete. There's water sorptivity test which measures the water penetration ability of concrete, and there's RCPT which measures the resistance to penetration of chloride ions. Okay, now to set a pass or fail criterias on these durability indexes, we on these durability testing we have indexes. Okay, so you can see OPI, sorptivity, and conductivity, the different values can be observed from testing, and based on different values we can set different criteria. So whether it is good, bad, or we should reject, that criteria can be set based on the values that we observed from the simple durability testing. So this is what comes under this heading, durability index values, that is used to test concrete before construction for durability properties. Okay. Now, there are lots of tables and guidelines that are present in Indian standards for ensuring that adequate durability is considered while mixture design of concrete. So this slide has table related to minimum service life that we want from a structure. So like we have IRC 112 code which categorizes design service life of bridge into three categories. So there's normal design service life which is more than 100 year, which is used for all bridges. Then for temporary bridges we need a service life for 10 years or less, and there are some special applications for which we need a 20 or as specified by user service life. Okay, so based on the type of bridge and the condition of bridge, IRC code specify what service life is needed from the bridge. Similarly, we have IRS 1997 code. So this is a Indian Railway Standard code which also categorizes service life of bridges based on location. So the bridges which are near sea, we need a service life of at least 50 years. The bridges which are in the coastal areas, they need a higher service life, and the bridges which are present in rest of the India, they should have a much higher service life. So why bridges near sea has lower service life? Because they have more deteriorating conditions, so that's why we have demanded for a lower service life, so that proper maintenance and repair can be done from time to time. However, bridges which are not near any aggressive environments, they should have a comparatively high service life in them. Okay. Now there are based on condition also the aggressiveness of the environment, there are different classes in which the environment is categorized. So there is five classes of environment categorization that is there: mild, moderate, severe, very severe, and extreme. And all these three code, IS 456, IRC 112, and IRS 1997, they have given different conditions of of the concrete, of the exposure to consider in some category. So I'll just take one example, like you can see here in IS 456, for surfaces of member in tidal zone or member in direct contact with liquid or aggressive chemicals, they categorize those concrete surfaces under extreme condition. For different condition, they have given different environmental exposure. So based on the location of our structure and the exposure condition, we can categorize our condition into these categories. Okay. Now, once we have categorized the exposure class, okay, we have fixed the exposure class, we need to set some boundaries on mixture proportion to ensure adequate durability is achieved by the concrete. Now, these boundary limits that are set on three parameters: W by C ratio, cement content, and cover depth. Now, why these three parameter? Because first of all, W by C ratio, it governs the porosity of concrete. So higher is the W by C ratio, more is the porosity, so faster is the ion ingress. So that's why we set limit on maximum W by C ratio. Okay. Then you can see here, for different exposure conditions that we have classified from the previous table, different code says the maximum W by C ratio allowed. Okay, so ensuring W by C ratio below this value means that we are following the durability guideline of the standard provisions. Then there is limit on cement content. Okay, so cement content not only dictates the strength, but it also dictates the heat of hydration or thermal or shrinkage cracking in concrete also. So that's why there is a limit on maximum cement content in concrete, which is 450 kg per meter cube in IS code. However, limits vary on minimum cement content. So this maximum cement content is limit is same for all exposure condition, because it is related to the heat of hydration that is generated. However, they limit vary on minimum cement content because it governs the porosity of concrete. Also, okay, so that's why we have limits on minimum cement content. And for different exposure condition, there are different values that are mentioned in the code. And finally, cover depth. That is a very that is very normal to understand, because lower is the cover depth, it will make aggressive ions to penetrate deeper into concrete, and in case of reinforced concrete, it will help the aggressive ions to reach reinforcement sooner than expected. That's why we have a limit on maximum cover depth. Okay, this is minimum. Okay, that's why we have a limit on minimum cover depth. So the covered depth should be at least more than these values. Okay, that's what the limit has been set. So as the aggressiveness of the environment is increasing, the minimum cover depth values are also increasing. Okay, and that you can see varies with the type of structure element also. Okay, in various exposure conditions. Now there are limits on initial crack width also, that is mentioned in IS code, because if there is wider cracks initially, even though we have followed all the design parameters properly for W by C ratio, cement content, and cover depth, still ions can easily penetrate through cracks. So that's why different code has different say on this. So like IS code, it has a different say on crack width, whether it is a concern, not a concern, or a severe concern. IRC code also mentioned for different exposure environment what is the limit of crack that should be present on the surface, and IRS code also mentioned for different exposure environment what is the limit of crack can be there on the concrete. Now, finally, there are limits on the aggressive ions that are there in the concrete. So, we have maximum limits of chlorides and sulfate because these are the main chemical degradation ions. So, we talked initially, if there's more chlorides in the concrete itself, that is inside concrete, that can lead to earlier corrosion inside the concrete. So that's why there is limit on maximum chloride that is mentioned on different types of concrete uh, in IS 456. Similarly, there is limit and mentioned in IRS and IRC code also for different exposure condition. What is the limit of chloride ions inside the concrete? And similar limits are mentioned for sulfate ions also. So for sulfate, the main source is ground underground structure, where concentration can vary based on the soil and the groundwater. So that's why for different types of concentration of sulfate in soil and in groundwater, different types of cement recommendation is mentioned in IS code, and along with the recommendation of mentioned on grade of concrete, cement content, and maximum W by C ratio. And for freeze and thaw resistance also, some limits has been mentioned in is code, is 456. Okay, so based on maximum aggregate size, what is the maximum amount of air and treatment that can be in the system is mentioned in is code. Okay, so just based on this durability criteria part, try to answer this simple case study. Any doubt in this final part, like different tables, different design codes, what are they saying, why they are saying these things? So can anyone answer this question? So this is a case study where a reinforced concrete bridge is proposed near a coastline in a region exposed to high chloride environment. Okay, the design life is 100 year and the structure includes both cast in situ and pre-stressed concrete element. Now, given the exposure condition, which concrete gate and water cement combination we should follow? Okay, so if I follow I is 456, I have this table, okay, which is mentioned. Okay, now which exposure condition is my concrete in? So if you see this table, it is in tidal zone, and in tidal zone comes under the environmental condition of extreme. So for extreme, what limit is mentioned? I need a W by C ratio of zero point 0.4 and a minimum concrete of M40. So M40 is generally like, I have not mentioned here for grade, but it is M40 grade that is generally used for coastline regions. Okay, that this is also mentioned in is code in some table. Okay, if you go through is 456, you will see based on exposure condition they have also mentioned which grade of concrete needs to be used. Okay, so this is how we read the tables. So from the this keyword we got to know that our structure is in extreme condition, and then we went to the table which sets limits on different parameters to get the answer. In IRC 112, how should the durability be enhanced for a 100-year long, 100-year design life? Okay. So what IRC code says to enhance durability? Okay. So yes. So the correct answer is C. So IRC code, it is more oriented towards having lower permeability concrete and increasing cover of concrete. Okay. So that is their main basis for ensuring higher durability of concrete. Okay, so this is how we read the tables. Okay, from each of this table we get some insight of the durability parameter, and these tables are interlinked to each other to get the different conditions or criteria set for concreting to ensure that concrete is of good quality. Okay, so this was all about this week. We completely discussed the durability issues in concrete. We understood different transport mechanisms, different ions responsible for degradation, mechanism of degradation due to different ions, and how design incorporates durability. Thank you.